So, continuing with, let's get into 13.2. So we're talking about Le Chatelier's and shifting equilibrium. So we got a little bit into this. We saw a little bit of it in the lab. Right? We increased temperature, we decreased temperature. Right? We were noticing shifting right, shifting left if we added some concentration of some solution and shifting that. So, Le Chatelier's. Le Chatelier's, spelled it I-E-R. Yeah, Le Chatelier's. So Le Chatelier's principle relies on well, not relies on, but it's how a system deals with stress, right? Is what if we stress a system? Like, how is the reaction going? What's going to happen to the reaction, right? How does the specific system deal with that kind of stress, right? So what if Q is not equal to K because we've done something to it, right? Maybe we change the concentration of some solution. Right? Maybe we added more of some reactant or more of some product, and now the system has to relieve that stress in order to come to equilibrium again, right? In order to go get K and Q to be equal again, right? What if we change the temperature? Yeah. This adds stress into the system, right? How is it going to react to relieve that stress, right? Another one we didn't get to work on in the lab, but what about changing pressure, right? What happens if we stress a system by changing pressure, right? Is that what's gonna happen to that, right? So let's just kind of initially talk about, what the effect is on change in pressure. So the effect on change in pressure and how the system reacts to that. So let's just kind of propose some formula here. Okay. We have some nitrogen monoxide gas, plus we're going to add a little bit of O2 gas to that, reversible reaction, and we're going to get some nitrogen dioxide as a result. Right? So what happens if we increase the pressure? What I want you to notice here, I'm going to underline these, right? Everybody understands that there's an imaginary one here. Now, the system here, the reactant side, we have 3 moles of gas. Right? And then on the product side, right, we have 2 moles of gas. So we take 3 moles, and in order to make the product, we reduce those 3 moles into 2 moles of nitrogen dioxide. So if we increase the pressure here, this is what occurs, right? Is that 2 moles of gas, right, takes up less space than 3 moles of gas, right? Is that we squeeze this, right? We're increasing the pressure here, and we would see this reaction shift to the right to relieve that stress. Uh, right? So, and that's because of the increase in pressure, right? Because the increase in pressure is that we shift this reaction to make more product in order to relieve that stress. Now, if we decrease the pressure, right, just the opposite would happen. If we decrease the pressure, well, that's going to shift this reaction because now that there's more room from decreasing the pressure, right? Um, because there's more room there, we're going to decrease the pressure, and we would shift that reaction to the left, going from 2 moles of gas to 3 moles of gas. So when we think about, decreasing the pressure, we can also think of it this way, is that in order to restore the pressure, you know, um, in order to restore the pressure, right, is that we're going to just increase the number of moles there, right? The more moles we have is that we can just kind of maintain the pressure that it had before. So now we can talk a little bit about, change in temperature, right? So change in temperature, let's take a look at a different reaction for that. So what about change in temperature? So change in temperature, let's take a look at a reaction here. So how about just some hydrogen gas? We'll take some iodine gas. And let's go ahead and react. Then we get a reversible reaction going here. There we go. And this is also going to be some gas here. Okay. Now, this reaction happens to be exothermic. You don't know that. I wouldn't ask you to know that. Let me rewrite exothermic. Right. So, this is an exothermic reaction, and let's see, the enthalpy on this is going to be a negative 9.4 um, joules per Kelvin. Here's a exothermic reaction, right? So, exothermic reaction means that there's going to be heat as a product, right? We're releasing heat. Right? There is some release of heat here. So there's 4 ways that, there's different ways that we can change the equilibrium here, right? Change in concentration, change in pressure, change in temperature, and that's specifically what we're looking at here. So if we increase, right, increase the temperature, right? And we saw this in the lab, right? If I increase the temperature, if I'm adding more heat into the reaction, right? I'm adding additional heat into the reaction. It's kind of like adding more product into the reaction, right? If I added more of this iodic acid here, right, is that we would shift that to the left. Same thing occurs when we increase the temperature in an exothermic reaction. If we're going to be adding more heat, then we are going to shift this particular reaction to the left, right? Decreasing temperature, right? Decrease in temperature is that if I'm going to decrease the temperature, right, is then we're going to be shifting that to the right. So here, this is going to shift to the right. Uh, Endothermic reaction. So still with change in temperature, but let's look at an endothermic. So endothermic reaction. Let me see if I can get. I got an endothermic reaction. So about ammonia. Let's use ammonia. And we're just going to get some nitrogen gas out of that. Plus, we're going to get some hydrogen gas out of that. Let's balance this. 2 here. 3 here. And I think that balances this out, right? So endothermic reaction. right? Endothermic reaction, the enthalpy change in here is going to be 92 kilojoules here versus the 9.4 kilojoules that we saw above. So endothermic reaction, which means that heat is required for this reaction, right? So if I'm going to require, if we're going to be requiring some heat in here, right, we're going to be adding more heat here than here in an endothermic reaction. If we add heat, if we increase the temperature, is that this is going to shift to the right, right? Decrease temperature is that we're going to have this shift to the left. Now, still staying with this endothermic reaction here. So let's just kind of continue with this endothermic reaction. How about pressure here? All right. On the product side of this reaction, right, we have 4 moles of gas. And on the reactant side, we have 2 moles of gas. Right? Now, when we're back up here, right, if we increase the pressure here, right, increase the pressure, we're going to have we're going to need room for less moles, right? Is that we need to also increase the pressure. We need to decrease the number of moles. So here, if we increase pressure, pressure goes up, increase that pressure, is that this is going to shift the reaction to the left, right? We need 4 moles of gas is just too much space. So the system has to relieve that stress by pushing this reaction to the left. So we have less moles of gas with the increase in pressure. And then just the opposite. If we decrease the pressure, right, we have more room and we're able to shift the reaction to the right. Oh, let's see. How about one more? Let's go with one more. Maybe a couple more reactions. Let's keep going with this idea of shifting to the left and right, increase, decrease pressure. I'll give you the enthalpy here, and we can take a look at this here. So, how about some ozone? Okay. This reaction with ozone. Now, this is an exothermic reaction about negative 285 kilojoules. Now, let's increase the temperature, right? Exothermic reaction, if we're increasing the temperature, right, that means that heat is a product of this reaction. And if we're increasing the temperature, we're increasing the heat, we're adding heat to it, is that this is going to shift to the left, right? Decrease the temperature. Decrease the temperature, right? In order for the system to relieve that stress, we have to produce more heat, and that will shift this reaction over to the right. What about an increase in pressure? Right? Increase in pressure, right? We're going to shift. Increase in pressure, right? We have to decrease the number of moles. Increase in pressure is a decrease in the number of moles, so we're going to shift this reaction to the left. Right? Decrease our pressure. Right? This is going to shift the reaction to the right by decreasing that pressure. Right? So here, uh, we can take a look at what happens, when we talk about just simply just some global warming, right? And why we're creating so much ozone, right? Is that if the atmosphere in the earth, right, is gradually getting warmer. These greenhouse gases are just getting increasing the temperature, right? Is that this reaction, the result of that is that we create more ozone, right? By just simply the Earth warming up, right? Is that we're just naturally just making more ozone, which is really, this isn't great. So now let's take a look at concentration. Let's go back, let's talk about concentration. So let me give you changing concentrations here. So let's go, what's some methanol? This is a reaction for methanol. So methanol, let me respell that here. Sorry about my sloppy writing there. Or to make methanol, let's take some hydrogen gas, plus we're just going to take some carbon monoxide, and we're going to create some methanol gas. Let me balance this real quick. I think we're balanced here. Exothermic reaction, right? We just got the combustion of carbon there, but this exothermic reaction, minus 90.2 kilojoules. Now, let's see what's going to happen. What's going to happen if we add, right? If we increase, and when I'm writing this, when I write brackets like this, what this literally translates to is concentration. Just so you understand my shorthand writing that we're going to do, right? So when I write this arrow up, right, instead of writing increase, I'm just going to write arrow up, right? Arrow down, decrease, just so you can keep up with my shorthand. So what happens if we increase the concentration of this particular hydrogen gas here, right? So when this comes to equilibrium, right? We're not talking about it initially. I'm just going to start with hydrogen gas. We're assuming that this reaction here is at equilibrium Q. Okay? Now, at equilibrium, if we add some concentration of hydrogen gas, right? Is that what's going to be the effect of that, right? What happens if we maybe decrease the concentration of carbon monoxide, right? What's the effect of that? How about we increase the concentration of methanol? How about, we can change the temperature here as well. This is an exothermic reaction. So here, if we're at equilibrium, let's take a look at this reaction. Let's recall what we were doing in 13.2 when we were looking at Q equal to K, right? Q equal to K. So when we were looking at Q, we had a formula here where we wrote concentration of the products over concentration of the reactants. Right? So in order to figure out, we're going to talk about what we call K sub C, right? So this is the equilibrium constant for concentration. And if we assume that K is equal to Q because we're at equilibrium, so our formula for that would be concentration of ethanol over our concentration of hydrogen gas. And then we have to make a note of this here. And I'm going to put that in red over here as well. Right, just so we know what we're doing with that. And then we can go ahead and put on the rest of that. And we got the concentration of carbon monoxide. And we would be able to, determine what this is. Okay, so by increasing, right, if we increase this concentration here, right, is that this reaction would shift to the right. If we, but we know what direction this is shifting. Right? But there's other stuff involved when the reaction shifts because we made some change. Right? If I add hydrogen gas and we increase that concentration, we just talked about this, that this would shift in this direction. But at the same time that this is occurring, we will see a decrease in the concentration of carbon dioxide because in order to make more methanol, in order to make more methanol, for every 2 moles of hydrogen gas, we consume 1 mole of carbon monoxide. So if we're going to be shifting this to make more product, it would absolutely make sense that this concentration here will decrease. And that this concentration, because we've shifted this reaction to move to the right, is that this concentration here increases. Right? So that's the result um, of what happens here. Okay, so that's our result. So there's other factors involved other than just knowing which direction these reactions are going to shift, right? Is that we're gonna broaden this, right? So I think we have a good understanding of what the effect is by adding, removing some concentration of some reactant product, right? Increasing, decreasing temperature, increasing, decreasing pressure. But along with that, what is the result of that so that we can determine what K is not at equilibrium, right? We know how to calculate Q, right? We did those calculations. If we know that this reactant's at equilibrium, we know the concentrations, so we can calculate this. This is going to bring us into some idea of what we call ice tables, right? Now, ice tables, you know, we have to let's see. This is where we're going to begin learning what we call ice tables. Now, get a good handle on ice tables. There's different scenarios that we're going to be running through over the next 5 chapters, I believe it is. Like there are 4 or 5. I think we're going like 4 chapters at least with different scenarios. So we're talking about ice tables in this chapter, chapter 14, chapter 15, chapter 16. I think it's in chapter 17 as well. But get comfortable with what we consider to be ice tables, right? So this is where we start learning. So ICE is just an acronym for what we're going to be doing here, right? ICE is our initial concentration, I, and then C is some change in concentration that we're going to make. And then E is the concentrations when we reach equilibrium. So we'll start off small, right? Is that the first thing we're going to do is just kind of learn how to determine relative changes in concentration, right? So that's kind of our first step into understanding how we're going to build these ice tables, right? So the first thing we do is we need to determine relative changes. So let's take a look at some reactions. So we're gonna use X in order to help us determine what we consider to be relative changes in concentration, right? So X is just a symbol that we're going to use, right? It's just a symbol that we use in order to determine changes in concentrations so we can make calculations later. Okay, so X is just a variable that we're using. So let's start with just this reaction here first. Um, we got some methane. And then I'm going to provide you with some information as well. So this isn't information that this isn't information that would be provided. I wouldn't ask you to automatically know. So we understand that this is a reversible reaction. We can start with the reactants. We can start with the products. We can start with the reactants and the products in order to come to equilibrium. But here, let's say that we are going to, let's say I have an initial concentration of this reactant and an initial concentration of this reactant. Now, in order to make the product, right? If I just start with this and this, and I have none of this, the reaction has nowhere else but to shift to the right because I don't have any of it. Right? So this isn't at equilibrium yet. I'm going to start with the reactants. The reaction will shift to the right. So as it's shifting to the right, it's going to consume the reactants. So as far as our value of X is concerned, we're going to write minus X because that reactant is going to be consumed in order to shift this reaction to the right. And because of this 2 here, we're going to put minus 2X. The reaction is going to shift to the right. It's going to consume these reactants, and it's going to make the product. Right? So again, X is just a variable. Okay, we haven't solved for X. We will learn how to solve for X, but for now, we're just learning how to build an ice table, and this is part of what we learned to build an ice table. So let's take a look at another reaction. Propane plus some oxygen. We're going to get some carbon dioxide, plus we're going to get some water. Let's balance this. Let's go 3 here, 4 here, and 5 here. All right. So again, we're going to assume that we are starting with propane and with oxygen. Okay. It's going to consume this, so I'm going to put minus X. And because of this 5 here, we're going to write minus 5X. And then we have our reaction over here. It's going to produce 3X, and it's going to also make 4X. So positive 3X, positive 4X. Now, I should have put the reversible reaction arrow in here. So let me fix that. Reversible, reversible. All right. Let's look at another reversible reaction, but we have to think about this. We're going to think about this one a little bit differently, right? So here, if we start with this, and we don't have any of this, we don't have any of this, right? This is a reversible reaction, which means if we start with the product here, we're going to shift the reaction over to the left, which means it's going to consume this. This concentration is going to go down because we're shifting it over to the left. So here we're going to write minus x, and then this would be plus x, and this would be plus x, right? So we really have to think about what our starting um, products and reactants are in this reaction. Okay. All right. Oh, let's see. Calculating some equilibrium constant. Let's take a look at some values here. Let's take a look at some values. Um, let's go. How about SO3? We're going to make SO2 plus an oxygen. All of these are in gas phase. Let me just let me balance this. There's 6 oxygens, 4 oxygens, 10 oxygens. We're good. Okay, yeah, so I think we're good here. Two. Yeah, we're good. All right. So let's go with our relative. Let's assume that this reaction is going to shift to the yeah, let's say this is going to shift over to the right. So this is going to be minus 2x. This is going to be plus 2x, and this will be plus 5x. Now, the concentration, so the concentrations here, let's determine what K sub C is. So let's determine what K sub C is. So K sub C, products over the reactants, right? This concentration here, SO2, and then don't forget this here. I'm going to underline it in blue, and then I'm going to write it in blue over here. Times the concentration of O2. I'm going to underline this in blue, and then I'm going to write this in blue over here. And that's going to make our reactant, this concentration, SO3. So if we were to figure out Kc here, right? If we were to figure out Kc here, let's go with if the concentration of SO3 was equal to 0.250 molar, the concentration of SO2 was 0.250 molar. And the concentration of O2, let's say it's 0.125 molar. Right? So we can plug in all of these values here, right? We can plug in all of these values here. Let's go. K sub C is then equal to 0.250 squared times 0.125 to the fifth over 0.250 squared. I'm going to do some cross canceling here so we can actually cross cancel this. And then our answer is going to be here. And we're going to 0.125 to the fifth is going to equal K sub C is 3.1 times 10 to the minus 5. Uh, and just as a reminder, right, K sub C is less than 1, right? So here, because it's less than 1, is that we're going to have more, right? Not a spontaneous reaction, is that we're going to have more reactant than product. So our reactant is greater than the product here, right? We just learned that from the other chapter as well. All right, continuing on, let's take a look at another problem here. So we're getting familiar, right, with some of these reactions that are going on. Um, you know, reintroducing, K sub C less than one, K sub C greater than one. Um, Reintroduce the idea of exothermic, endothermic reactions, um, reactants that are at equilibrium, reactants that are not at equilibrium, shifting reactions, changes in concentration, temperature, pressure. The only thing we haven't done, and before we start again, before we go further into building ice tables and making some calculations, is shifting reactions, right? Le Chatelier's principle when it comes to acids and bases. Right. We'll talk about this again more in chapter 14 because that's where we're going to have acid-base equilibria. But I do want to introduce before we get to that chapter. So let's take a look at maybe a reaction or two, and then we'll start building our ice tables just to make sure we're understanding Le Chatelier's and how this shifts here. So let's take this reaction here. So let's go back with ammonia plus some water. And we're going to get some ammonium. Plus, we're going to get some hydroxide here. Now, uh, there are certain things that we can do with this. We could maybe add some hydrochloric acid, right? What's going to be the effect? Maybe we'll add a strong base, not just a strong acid, but maybe we'll add a strong base. Some sodium hydroxide. Okay, how is the system going to relieve the stress of adding a strong base? About we add some ammonium chloride. What is the effect going to be if we add some sodium chloride? All right. So when we think about this, and again, we did see this in the lab. We did talk about this when we're looking to add. How about we add some hydrochloric acid right into this reaction? What would happen? Well, when we add hydrochloric acid, this strong base, and what we're going to get is we're going to get some hydrogen protons, plus we're going to get some chloride ions. Now, the chloride ions, right, is that these are what we're going to consider to be a stand, right? We consider these to be a bystander. That's the word I'm looking for, a bystander ion, right? Nothing. The chloride doesn't affect this reaction, but if we add hydrochloric acid, and this dissociates, well, the hydrogen protons definitely affect this reaction. So definitely so much is that when we take a look at the reaction for water, hydrogen proton ions plus the hydroxide ions make a water molecule. So by adding hydrochloric acid, it will consume the hydroxide. Right? And if we consume that hydroxide by adding chloride, we're going to have a shift to the right simply because we're consuming the hydroxide. Is that in order to relieve the system, is the reaction has to shift to the right in order to produce more hydroxide. So that would be the effect of this over here. Now sodium hydroxide. If we add some sodium hydroxide into the reaction, all right, let's take a look at that. So if we add sodium hydroxide, strong base into the reaction, it's going to dissociate into some sodium ions and some hydroxide ions. So the sodium ion is a bystander ion. It's not going to affect the it's not going to affect anything in the reaction. But the hydroxide, right? If we're adding more hydroxide, we're increasing this concentration. And by increasing that concentration in order to relieve the stress, is that this reaction will shift to the left, right? In order to come back to equilibrium. And then lastly, if we add ammonium chloride, right, this will dissociate. We're going to get some of these ions, plus we would get some of these ions. There's our bystander ion, and this would have an effect on the reaction. If we increase this concentration here, if we increase this concentration, right, is that in order to relieve the stress, again, we would shift left in order to relieve that stress. Right? So things to think about when we're looking at acid-base reactions for this. We could probably take a look at one more real quick. How about we take a look at one more? Let's spell about some acetate. So here's some acetate, and if we put acetate in some water, this is a weak acid. Put that into some water. We're going to get some hydronium ions. Plus, we're going to get some acetate. All right. So, but again, what we'll add, let's add hydrochloric acid. Let's add sodium hydroxide. So if we add hydrochloric acid, if we add strong base, sodium hydroxide, if we add, how about this time we add some sodium acetate? Let's add some sodium acetate to that. All right. So here, if we add hydrochloric acid, essentially this is what we're adding. Okay. Um, one more reaction here that we need to be familiar with is that this plus this um, make this. There we go. So this is another reaction, right? And again, this also makes water, right? But when we're looking at these reactions here, let's make an equivalent here. Let's say that if we add H plus, it's equivalent to adding H3O plus. Right? This is an acid. This is an acid. Right? And they both make water molecules. Right? We can see from this water, right? This makes water. And in our previous reaction, we also made water from that. Right? So let's just say that those are equivalent shows that if we're adding those, so but essentially if we're adding the HCl, we're adding this, which means that we're going to shift this reaction over to the left, right? Because we're increasing this concentration here. Now, if we add sodium hydroxide, if we add sodium hydroxide, well, we're getting this and we're getting this bystander ion, but we are increasing this concentration, right? If we're adding this, if we add this, it's going to consume this to make some water. So that means that this concentration will now start to decrease. And in order to relieve that stress, we have to produce more of it. So by adding that, we're going to shift the reaction to the right in order to relieve that stress. Now, if we add some sodium acetate, right, the sodium we're not going to worry about, but the acetate here, right, that means that we're increasing this concentration here. Relieve the stress is that we're going to be, you write a double arrow here, double arrow, is that we're going to shift the reaction to the right. Right? So those are just the effects of adding some acid or some base, into these reactions here. Okay. Now, let's take a look, and I guess we're at the point now. We should start building some ice tables, right? We're going to start building some ice tables. Okay. We take a look at this reaction here, and in this reaction, we're going to add a concentration. Let's say this here, right? This concentration is what we're gonna start with this concentration here. We're going to start with this concentration here. Now, when we build ice tables, we're gonna literally write the word ice out. We need to keep track of everything, right? Everything here is going to be in some columns here, and we're going to need to record everything. So when we were practicing relative changes in concentration, we're using x, right? Minus x minus 2x x, right? Plus x minus x. And this all depends on the starting material that we have. So we have our reaction, right? So now ice, I for initial, right? What are the initial concentrations? So let me write it on the outside instead of the inside like that. So I for initial concentrations. Okay. So the initial concentration of I2 is 1.00 times 10 to the minus 3. And these concentrations we're assuming are in molarity. So concentration in molarity. And our the next one, our initial concentration is 1.00 times 10 to the minus 3. And now our initial concentration of the product, we're only starting with these two. Our initial concentration is simply just 0 here. So what change are we making here? Well, we don't know what change we're making yet. So this is where that X value, right, is going to come in, right? So our change, C for change, is that this is minus X, this is minus X, and this is plus X. And in order to figure out what the equilibrium concentration is we're going to put these two together now. Now we have 1.00 times 10 to the minus 3 minus x. 1.00 times 10 to the minus 3 minus x. And here we have 0 plus x. So 0 plus x. All right, so let's take a look at what we have now. So now we have to solve for x. Right? We do have some additional information here. Now, the information that's also provided to us is what we call, let me erase that here. The additional information here, what we have is we have the equilibrium concentration. So the equilibrium concentration is 6.61 times 10 to the minus 4 molar. So this is what our equilibrium concentration, and this is the equilibrium concentration of I2. So in order to figure out what our equilibrium concentration, right? In order to figure out what X is, if I know what the initial concentration is, and I know what the equilibrium concentration is, that will help us find out what X is. Because this is the only way that we're going to find out what this concentration here is. If we can find out what X is, we can get the equilibrium concentration. Actually, there we go. Once we find out what the equilibrium concentration or what that X value is, we can determine what the equilibrium concentrations are for everything else. Okay, so how we can set this up is we can say, well, using this information here, we can say 1.00 times 10 to the minus 3 minus X is equal to 6.61 times 10 to the minus 4. And then if we solve this, X is equal to 3.39 times 10 to the minus 4. So now we know what this X value is. So once we know what that is, well, now we can figure out what the equilibrium concentration of this is, and we can figure out what the equilibrium concentration of this is. So we can see that I minus, right, this iodide, right, that concentration is equal to the concentration of the iodine. So those concentrations are equal to each other. So we can say that that is also going to be, we can do the math for it, and we could just say 1.00 times 10 to the minus 3 minus 3.39 times 10 to the minus 4, and that's also going to equal 6.61 times 10 to the minus 4. And then for I3 is simply 0 plus x, which means 0 plus 3.39 times 10 to the minus 4. So that is going to equal 3.39 times 10 to the minus 4. So when these all come to equilibrium, if we start out with these here, when this comes to equilibrium, where K is equal to Q, we now know the concentrations at equilibrium. At equilibrium. All right. Before we move on, right? Now that we know these equilibrium concentrations, we know this concentration, we know this concentration, and this is equilibrium concentrations. So Q, let's talk about Q sub C. So if these are at equilibrium, then K sub C is equal to Q sub C. And we can figure out Q sub C by products over the reactants. Products concentration, so we have 3.39 times 10 to the minus 4 over 6.61 times 10 to the minus 4 times 6.61 times 10 to the minus 4. And we can figure out what this is. So we put this in the calculator, and we see that our K sub C is equal to 776, right? Spontaneous reaction, absolutely. Here's that K sub C is greater than 1. And it's a lot greater than 1. So this is a really favorable reaction that we have here. Okay? Favorable reaction that we see there. Right. So ethanol and acetic acid. So I'm going to give you some information here, but first let's go with the information first. Right. So I have 1 mole of ethanol. Ethanol is C2H5OH. I also have 1 mole of acetic acid. And these are in a 1 liter a 1 liter solvent of dioxane. They're in a 1 liter solvent. The dioxane is not really important, just that we need to know that it's in 1 liter. When we look at ice tables, let's take a look at the reaction. So let's build the reaction. So here's our reaction here. And initial concentrations here are in terms of molarity. And I have 1 mole per liter, making this 1 molarity, right? Because that's what molarity is, right? Let's recall that molarity is moles over liters. So all of these that are in all the concentrations are molarity. 1 mole divided by 1 liter equals 1 molarity. So these are initial concentrations that we have here. So here's this initial concentration here, which is just going to be 1. And then the concentration for the acetic acid is also going to be 1. Our concentration of the products, this is 0 and this is 0 here. So water here is a solute. We're not using it as a solvent. So the solvent is a dioxane. Solute, the water here is a solute, so that concentration is going to be affected. Okay, so what is our change here? Our change is going to be -x, plus x, and plus x. Now, in this problem, equilibrium equilibrium is reached when 1/3 moles of the reactants remain. This is really important information for this problem here. Okay. On the exam, I'll make it pretty explicit, and I don't like working with fractions, but we're going to have to work with fractions here to get this one solved. But here, equilibrium is reached when 1/3 mole of the reactants remains. Okay. So that's pretty important for us. And here we have our equilibrium concentration. So equilibrium concentrations, 1 minus x, 1 minus x. This is just going to be x, and this is just going to be x, right? I'm not going to put 0 plus x. I'm just going to put x. But if equilibrium is reached when 1/3 moles of the reactants remains, well, 1/3 in a 1 liter solvent solution is 0.33333 molar, or we could just say 1/3 molar. So we know what the equilibrium concentrations are for both the acetic acid and for methanol, is that 1 minus x is going to equal 1/3. 1 minus x is equal to 1/3, which means that x is equal to 2/3. So we know this. So x is now equal to 2/3 because, and then from this, once we know what x is, well, there we go. Now we know all equilibrium concentrations. So in order to figure out K sub C, which this problem was asking us to do, K sub C is our products over the reactants, products over reactants. So 2/3 times 2/3 divided by 1/3 divided by 1/3, and this goes 2/3 divided by 2/3, calculator, and this is going to be 4. So here, K sub C is equal to 4. So we were able to, again, figure out what K sub C is, provided we were given equilibrium concentration. So in the previous problem up here, right, is that I provided you with one of the equilibrium concentrations. We were able to figure what solve for x, right? We solved for x here. And then we calculated K sub C. Again, we were provided with the equilibrium concentrations. Equilibrium concentration was 1/3 mole when 1/3 moles of the reactants is left. So we go from 1 liter, I'm sorry, from 1 molarity to 1/3 molarity. And again, we're able to determine what K sub C is. So what about problems? What about problems when we're not given the equilibrium concentration? Right. Right. So let's make a calculation regarding that. So calculations without the equilibrium concentration. I'm just going to label that here so we know what we're doing. So calculation without any equilibrium concentrations given. Right. They will have an equilibrium concentration, but we have to determine what that is, right? Where before they were given it to us, right? So let's get some information here. So here, in order to do that, but we can't figure this out unless we're given some information here. So we're going to have to work this a different way. But I'm going to give you K sub C. So K sub C is 0.0211, and that's our K sub C. And then we're going to have an initial concentration. Initial concentration of this is going to equal 1.00 molar. And this is going to be our reaction here. It's going to go to P. That's a 3. All right. So this is our reaction. So let's build our ice table. And again, try and understand ice tables. Get used to doing ice tables. We're doing it in the homework. We'll do it on the in lab or on the examples. I think we have a lab or two that has to deal with this, but we're going to be doing ice tables for the next 4 chapters, right? So we have to learn this. Okay. All right. So we do have an initial concentration. That's what this is. Initial concentration. It's already given to us in molarity. So we're going to put 1.00. And our initial for the product is going to be 0, and this is going to be 0. This is going to be minus x, plus x, plus x, 1.00 minus x. This is x, and this is x. Okay. So now that we have that information, right, we do have what K sub C is. The formula for K sub C, products over reactants. Product X, concentration of this one, concentration, those two concentrations here, right? These two concentrations here, products, over our reactants, 1.00 minus X. Right? So these are where these values are headed towards. Right? But we were given some information here. So let's try and begin the calculation here. It's probably going to be quite lengthy. Let's see. So we know what K sub C is. So I'm going to put 2.0211. This is our K sub C, is equal to x squared, which is x times x is x squared, over 1.00 minus x. Now, with some algebra work, right? With some algebra work, we have x squared minus 0.0211 times 1 minus x. All right, all we did was just a little bit of algebra work here. All right. Now we need to multiply this out. So let's go with x squared minus 0.0211 x 0.0211 x minus 0.0211. Right. So what we're needing to do now, you're probably not going to be too happy, but we're going to need the quadratic equation for this, right? The quadratic formula, right? I hope we all remember the quadratic formula. It's coming back to haunt us, where x is equal to negative b plus or minus square root of what is b squared minus 4ac. This is going to be all over 2a, right? So this is our quadratic formula here, and this is what we need in order to solve this quadratic equation. If you have a calculator that'll do it, you get the TI 36X Pro, it'll solve quadratic equations. And I don't mind you using those to in your calculator, right? If you have a calculator to solve it, great. If not, you're gonna have to do it longhand, unfortunately. Okay. So let's figure out what x is here. So x X is equal to negative 0.0211 plus or minus square root of 0.0211 squared minus 4 times A 0.0211 2AC, uh, which is going to be 1 all over 2 times 1. I did miss a negative sign, so let's actually put that back in here. So this is negative, right? So I did miss that. So let's go ahead and calculate this out now. Let me throw this in the calculator. So by putting that into the calculator, we're going to come out with this answer here. So we have two answers for this. This is going to equal a negative 0.156, or, right, x is equal to negative 0.156, or it's equal to a positive 0.135. So which one of those do we use? Well, let's look at the problem that's going to help us figure out what the equilibrium concentration is, because all we know what the value x could be. So the concentration is either equal to 1 minus 0.135, or it's 1.00 minus negative 0.156. So this helps us determine what these concentrations are going to be. If we use this one down, let's start with the negative 1.15. So this is going to be 1.156 as the concentration. Right. So that doesn't seem to make any sense, because if the concentration is going down, it wouldn't make any sense for the concentration to be higher, right? So now let's take a look at the other one here that we have. So now that we calculate the other one, the other one is just going to be 1 minus 0.135, right? 1 minus 0.135, this is equal to 0.865, and that would make a lot more sense, right? So we're not going to be using this value here. We know that x is equal to 0.135. So as far as the final concentrations go, right, we know what x is. So our concentration, let's put all the concentrations here. These are all equilibrium concentrations. So the equilibrium concentration for PCl5 and for PCl3, for Cl2, this concentration is equal to what X is. 0.15, no, 0.135. 0.135. This is also equal to 0.135, because those are what equal to X is. Now for the PCl5, it's 1 minus that. So 1 minus 0.135 is equal to 0.865. And these are the equilibrium concentrations. Okay. So we're going to be doing some more, right? Well, we're definitely going to be doing some more of these. And again, when we hear equilibrium constant, what we're referring to is K sub C. So K sub C here, the equilibrium constant, is equal to 4.0. And the question is asking us, what are the equilibrium concentrations for the mixture, right? So initially, we do have some initial concentrations. So the initial concentration of acetic acid looks like this is equal to 0.15. And our initial concentration of methanol, oh, ethanol, 0.15. We do have an initial concentration of this is equal to 0.40 molar. And then we also have a concentration of some water here, the solute, not the solvent. And it's also equal to 0.40. So in this example here, is that we're starting with all the concentrations here. So what are the equilibrium concentrations? Yes, we're going to throw all of these in here. Let's get our formula together here. And there's also just one more piece of information that I don't want to forget. But let's get this reaction here. So we have CH3CO2H plus C2H5H. We're going to get the last piece of information here is I'm also going to give you Q. Q is equal to 7.1. Q is equal to 7.1. So why is this information important? Well, that Q is greater than K sub C. And with Q being greater than K sub C, this reaction shifts to the left. So if this reaction is shifting to the left, so when I put all of these in there and Q is greater than K sub C, because this is not at at equilibrium, Q is greater than K sub C, is that this, in order to come to equilibrium, the reaction is going to shift to the left. So when we're doing our ice table, this becomes very important when we're doing when we're drawing our ice table, because again, we have to think of negative X and positive X and where those values are going to be. Okay, so first let's get our concentration. So our initial concentration 0.15, initial concentration 0.15, initial concentration 0.40, 0.40. Now the change that's occurring is this is minus X and this is minus X because this reaction, again, just as a reminder, this reaction is shifting to the left. So this is going to be positive X, this is positive X. And now our equilibrium concentrations can be calculated by 0.15 plus X, 0.15 plus X, 0.40 minus X, 0.40 minus X. So the calculation for our K sub C, we do want to know what it is, but we just want to set up this formula first. Products over the reactants. We have this, and they're identical. Okay. So we're going to put 0.40 minus X. And instead of doing this, I'm going to write it, but I am going to erase it real quick. 0.40 minus X. So I don't want to write that out. What I do want to write out is just 0.40 minus X squared. And I'm going to do the same thing for the bottom. I'm going to put 0.15 plus X squared. All right. So in order to calculate this out, right, is again quadratic formula, right? Quadratic formula. I'm not going to be calculating quadratic formula. We showed you that. That's if you need to remember how to do it, either review this or go back and review how to do quadratic formula. So what I'm going to do is I've already calculated this out, and X is equal to minus 2 plus the square root of 4.84 over 6. And X is also going to equal negative 2 minus the square root of 4.84 over 6. So X can either equal 0.033 or X can equal negative 0.7. Right? So now we're able to determine what this is going to be. Now, if we're using negative 0.7, this is what happens when we use the negative. So I'm going to use this just to kind of explain what's going on. So if we know what X is, 0.15 minus, or I was going to say plus a negative zero point 0.7. This is going to give us some negative value, right? We don't have negative concentrations. So we know that X is not equal negative zero point 0.7. It is going to equal just a 0.033. Right? So we can put the concentration is equal to 0.15 plus 0.033, which is equal to 0.18. 0.183, but just 0.18. And we can do the same thing for this one. So this equilibrium concentration that we're going to look here for ethanol, C2H5OH, is also equal to 0.15 plus 0.033. So it's going to equal 0.18. And our concentration for, and again, these are equilibrium concentrations. 0.40 minus 0.033, which is equal to 0.37. And then this water here, concentration of our water, our solute, is also equal to 0.40 minus 0.033, which is equal to also again 0.37. So we do have all those concentrations there. Right? Oh, more and more. We need more practice with this. More practice as we keep going here. Let's go with another problem. We'll get another problem. There's going to be some additional ones that I think I have that you'll probably like better, but we do need at least one more with the quadratic equation. So there are quadratic equation is not required all of the time. Right? There are some exceptions, but I just want one more ice table based off of using quadratic equations. So let's take a look at this example problem over here. So yeah, this example, this comes from example 13.9, where it says check your learning. So we can, if you want to take a look at that and follow along. So here, this is I'm just gonna write some information, right? We have a 1.00 liter flask. And that contains 1.00 moles of H2 and 2.00 moles of I2. So before we even get started, in order to figure out what the concentration in molarity of H2 is, right? 1 divided by 1, because it's moles per liter, 1.00 molar. Our initial concentration of I2, 2 divided by 1 is going to be 2.00 molarity. So that's just kind of the first step there. The value of the equilibrium constant. So our equilibrium constant, our K sub C, from this reaction is going to be 50.5 under these conditions. So now it's asking us to calculate what are all of the equilibrium concentrations for H2, for I2, and for HI, right? In molarity. What are these concentrations here? So again, this is initial, just as a reminder, right? This is initial concentration. This is also initial concentration. And it's asking us to calculate the equilibrium concentrations. Okay. Equilibrium concentrations based on, K sub C, not Q, but K sub C. So our reaction for this. So our reaction for this, they've provided, so we got H2 plus we have some I2, and we're going to get HI, and we do have this 2 here to deal with now. So this is kind of the first time everything's been based off of a 1-to-1-to-1 value, and finally we have this 2 here that we do want to be cautious with when we're writing our ice table. So here's our ice table. Initial concentrations: 1.00, 2.00, and this is going to be 0. The change, because we're starting with the reactants, minus x plus 2x. And the change here, in order to determine our change, we're going to go 1.00 minus x, 2.00 minus x, and this will just simply be 2x. So now we'll set up our value for K sub, our formula for K sub C, products over the reactants. And we're using these values down here. We're going to use this, we're going to use this, and we're going to use this. And we're going to put those into this K sub C. Okay. So when we're writing K sub C, we use this here, but we also need to use it in this formula. We discussed this earlier today, or earlier in this lecture here, when we're looking at these values here. Right. We did a previous 13.2. I'm going to highlight this area real quick. Right. This 2 here, this 2 here. This is K sub C. Right. So let's take a look at this problem as we're careful with it. So we're going to pay attention here, and we're going to put that this is 2x squared over 1 minus x times 2 minus x. 1 minus x, 2 minus x. Right. All right. So I'm not going to simplify this. Is that you're all able to do some algebra, and I end up with 50.5. That's what K sub C is, and then I ended up with let's see, is 2x squared over x squared minus 3x plus 2. Right. So I determined that x, I had 2 values for x, and determined that x is equal to 0.935. So in order to figure out the equilibrium concentrations, we're going to go 1.00 minus 0.935, 2.00 minus 0.935, and then we're going to go to times 0.935. Right? So I'm getting all of that information from here in order to determine what these concentrations are. So the concentration of H2 equal to this, concentration of I2 is equal to this, and our equilibrium concentration of this is equal to this. So this is going to be equal to 0.065. 2.0 minus 9, but it's going to be 1.065. And then this is going to be equal to 1.87. All right, so these are going to be the equilibrium concentrations. And again, if you're getting lost with solving these polynomials, quadratic formula, crack open your math book, get some help from the math tutor on figuring this out. I don't reteach college algebra here, okay? So you're just going to have to try and either get some help with that. Maybe ask me during the lab. We can practice some of this during the lab. But definitely let's work on these algebra skills here. So K sub C in this case is going to equal to 1.8 times 10 to the minus 5. Right. Now this is like a 5% rule for K sub C. Right. So there's rules for K sub C when K sub C is a lot less than 1, and when K sub C is a lot greater than 1, is that sometimes we can ignore some of these values when that's the case. So let's see. Let's start out with some information here. So let's go with some initial concentration of ammonia, and that's going to be 0.25 molar. We have our K sub C value already. And let's get the reaction here. So our reaction is going to be, we're going to take some ammonia, plus we're going to have water. You know, this is aqueous. So this is in water. Water's our solvent here. Water's not the solute. Water is our solvent. And there's a big difference when it's the solvent. So when it's the solvent, when we see water as a solvent, when we see water, liquid, we're going to ignore the value for water, right? We're not going to worry about that concentration because it is the solvent. It's not the solute being dissolved. Okay. Now, initial concentration we have here is 0.25. Uh, this is 0 and this is 0. Our change here is this is going to be minus x. This is going to be plus x, and this is going to be plus x. So the equilibrium concentrations to determine that will be 0.25 minus x. This is going to be x, and this is going to be x. So now our formula for K sub C. The formula for K sub C in this one is actually not too difficult. Products over the reactants, right? X multiplied by x. So we know where I'm going here. X times x is equal to x squared. So x squared over 0.25 minus x. 0.25 minus x. Okay. So what we can do here, all right, what we can do here is in this concentration here, I'm going to highlight this. In that concentration, because K sub C, this is 1.8 times 10 to the minus 5. 1.8 times 10 to the minus 5. This K sub C is definitely, it's not just smaller than 1, it is a lot smaller than 1. Okay? And because it's a lot smaller than 1, 20.25 minus 0.000018, because K sub C is so small compared to the initial concentration, is that we can ignore this X here. This X here, we can simply just ignore it. So if we know what K sub C is, and we're going to figure this out here. So K sub C, we're going to use 1.8 times 10 to the minus 5 is equal to x squared over 0.25. Right? S squared 0.25. And when we solve for x, right, I'm not going to again, I'm not going to rearrange this formula here. You guys can figure out what x is. Actually, well, here, let's do this. We're going to say 0.25 times 1.8 times 10 to the minus 5. The square root of that is equal to x. Right. So we know where we're going. But again, we should know how to calculate this. This is algebra. Is that x is going to be equal to 0.00212. So now we know the value of x. So when we're looking at our equilibrium concentrations, because this number is so small here, we could just simply say that the concentration, we know what the value of x is. So 20.25 minus this is still essentially 0.25. But the concentration of ammonium is going to equal this X value, 0.00212, and then our concentration of hydroxide, equilibrium concentration, 0.00212. So now we know all of those concentrations, right? 25 minus, let's do minus 0.00212, and I think this is like 0.2375. So here are all the concentrations. So just something nice that we can do when we're looking at those, when K sub C is either a lot greater than one or a lot less than one, is we can simply ignore that X so that we don't have to get into the quadratic formula. So let's look at one more, let's look at another reaction. Let's say K sub C is equal to 5.5 times 10 to the 8th, right? This K sub C is a lot greater than 1. So initially, we're going to start out with 0.25 molar. This is initial concentration of nickel 2 plus. I'm going to put initial here. Let's go with 2.00 molar ammonia. And again, this is initial concentration here. Oh, and let's get our formula together, our reaction. So our reaction is going to be, we're going to take nickel 2 plus, and this is going to be aqueous, plus 6 moles NH3. This is also aqueous. And that's going to give us some nickel ammonium. This is also going to be aqueous. So initial concentration, let's ice right here, initial concentrations, 0.25. This is going to be 2.00. This is 0. Minus X plus X. Oh, no, minus X. This is minus 6X. Let's back up here. Minus 6X. Then we're going to have 0.25 minus X, 2.00 minus 6X. And we're going to have, this is just X. So we know what K sub C is. K sub C is 5.5 times 10 to the 8th. So our model here, 5.5 times 10 to the 8th. 5.5 times 10 to the 8th, this is our K sub C, is equal to these products over the reactants. So it's going to be X. And because our K sub C is so small, we get to ignore this X, and we get to ignore this X. Okay? Otherwise, it'd be a real mess, but we get to ignore this. So we can put 0.25, but let's not forget this, right? This is going to be 2.00 to the 6th. And all said and done, here X is equal to 8.8 times 10 to the 9. 8.8 times 10 to the 9. So 0.25 minus 8.8 times 10 to the 9. And we're going to get negative. What do we get? Negative 8.8 times, like we get this ridiculously large negative concentration. We cannot have a negative concentration. Now, this reaction, 5.5 times 10 to the 8th, which is much greater than 1. When we have a concentration that high, we have to do what's called an all product starting point. Okay? An all product starting point. So uh, when K sub C is huge, right, is we need to do something called the all product starting point. Is that this reaction is so favorable, is that almost all of the reactant is gone. Okay. Nearly all the reactant is used up, and we make almost all of the product. So we just kind of have to think about this a different way. So we're going to redo this reaction. So as I rewrite this here, we're going to 6NH3, and then we got nickel, NH3, 6 of those. This is 2 plus. Okay, so stay with me here as we work back through this. Okay, we're going to assume that we're going to have 100% of product. Okay, and if we assume that we're going to have 100% of product, that means all of this gone. Okay, all of that's going to be gone. So instead of saying what our initial, if we're starting with the all product, we're assuming that this is going to be the reverse reaction, and we're going to have 0.25 moles. Okay. And the reason I'm using 0.25 moles is because there's no way, let me back this up just so we understand and we don't question this later. The product contains nickel, and it's 0.25 molar nickel. Why am I not using 2.00? Is because if I have 0.25 molar, there's no way I'm going to get 2 moles of nickel out of 2.25. So we use the smaller value there. Okay. So it wouldn't make sense to put this as 2.00 when we only have 2.25 moles of nickel. All right. Or molar nickel concentration solution. So we got the 0.25 here. So initially, we're going to have 0 here because, again, we're assuming this KC is so huge, we're assuming all product, and we have 100% product, and the product is going to be our starting point because this reaction is so favorable. Okay. So now we know what these are here. Okay. Well, the other thing we have to think of is that we have 2.00 molar NH3. So how do we determine that concentration? Well, since we have 6 of those, okay, what we can do is we can say 2.00 minus 6 times 0.25. And what this equals, so because we have 6 of them, 2.5, so 2.00, this is our initial. We can subtract 6 times 0.25, and this ends up being 0.5, so that's going to be our initial 0.5 here. Our change here, this is going to be negative x. This is going to be positive 6x. This is going to be x. So here we have x. This is going to be 0.5 plus 6x, 0.25 minus x. And we do have a huge K sub C, so we're going to be able to ignore some values here. So do they give us our K sub C? 5.5 times 10 to the 8th. Okay, so we're going to have 5.5 times 10 to the 8th is equal to products over the reactants, right? Even though we're starting with our product rule here, right? 0.25 0.25 minus x over x times 0.5 plus 6x. All right. So here we do get to ignore some values. What values? Because there's x's highlighted in a few different places. This x here, then there's 6x here, and there's 6x here. So the x's that we can ignore are the plus x's and the minus x's. So this we can ignore. This we can ignore. Okay. So the plus and minus x's from some value. Okay. So if we rewrite this, let's clean this up. We're going to have 5.5 times 10 to the 8th is equal to 0.25 over x times 0.5 to the 6th. And then we can solve this. So we do some algebra. X ends up being 2.9 times 10 to the minus 8. So once we know what that value is, then we can start putting in all the rest of these values here, and then ends up being, so concentration of nickel, equilibrium concentration of ammonia, and concentration of our nickel ammonia. Three, six. So nickel plus, because we know what X is, right? That's going to be 2.9 times 10 to the minus 8. And we know what that final cut, because we're ignoring this, we know what this is. So that's just going to simply be 0.25, right? And 0.5 minus 6 times this, 0.5 minus 0.5 minus 6 times 2.9 times 10 to the minus 8. So we can calculate that out of 0.499999999, so essentially it's still 0.5, that we can round that to. But these would be the equilibrium concentrations there. So, and again, as far as all product, well, you might see this on the homework maybe, but I do not have an all product rule on the exam. So, let's understand how it happens. But as far as exam goes, so I don't think I'm going to provide you with anything like that on the exam for an all product rule. Lastly, let's take a look how this relates to free energy. Right. Um, right. So Gibbs free energy, right? G. So, um, if we take a look at this equation here, so we did talk about this one already. So free energy is equal to negative RT natural log of K, right? And K here could be K sub C. R here is going to be value for R here is going to be 8.314, 8.314 joules per mole Kelvin, but because we're looking up K and K is unitless, I'm not even going to worry about the units there. So 8.314 joules per mole Kelvin. But we are able to use this if we have some information, we could relate free energy to this equilibrium constant for some reaction. Okay. So let's take a look at a reaction here. Let's take a look at this reaction. Here. Now, in order to determine this, we can look in the back of the book. So there's a couple different ways to look at this in the back of the book. There is another equation for delta G where we figure out what the enthalpy is, we figure out what the entropy is by doing um, the sum of the entropy minus the, sums of the enthalpy. But we're gonna take a little shortcut here, right? Is that this, right? The sum of products minus the reactants, right? Sum of the products minus the sum of the reactants. And that is our change. Okay. Now, if I provide you with some information, let's say delta G of, let's say NO2 is equal to 51.30 kilojoules per mole. And delta G for N2O4 is equal to 99.8 kilojoules per mole. Keep in mind we have this here. So as we're determining what this is, the sum of the product. So our product is going to be 99.8 minus 2 times 51.30. So we learned this in chapter 12. Okay. And this comes and this will equal 9.8 by 0, 99.8 minus 2 times 51.3. And we get products minus reactants. We get a minus 2.8 kilojoules per mole. Our constant is in joules. Our answer in free energy is in kilojoules. So this is actually going to be, I'm going to rewrite this as minus 2,800 joules per mole, because we do have to rearrange this equation here. So let's take this formula here that we learned in the last chapter, rearrange it because we want to solve for K. So we're going to say over negative RT is equal to the natural log of K. So let's input some of these values here. We know what the free energy is. So minus 2,800 joules per mole over a negative 8.314 joules per mole Kelvin equals the natural log of K. So let's see here. So we have negative 2,800 divided by 8.314 temperature. So temperature here, right? Temperature 25 degrees Celsius. Our temperature is going to be 298.15 Kelvin. This is going to equal, so we have 1.13 equals natural log of K. So math skills are needed. So we have to get out of this natural log here. We want to know what K is, not natural log of K. So in order to do that, we're going to put E to the 1.13. So E to the 1.13, this special Euler's number, E to the 1.13, and K is equal to 3.1. Now, I purposely did something here because we are going to calculate this one more time. Right? In your textbook, I've written this in reverse. Okay. So in your textbook, if you're looking at the example 13.14, right, it's not written this way. It is written N2O4, 2NO2, right? Because this is a reversible reaction. And the answer they give for K sub C is 0.32, right? So it's easily solvable. So again, products over reactants, right? How we solved this. Okay, products over the reactants is this would now be, if we use this here, in order to calculate this, products over reactants. So we're going to have 2 times 51.3. We will have 2 times 51.3 minus 99.8. So that gives us, let's see here, equals positive 2.8 or positive 2,800 um, kilojoules per mole. And this does have an effect on the final calculation. Right? So if we set this back up, we're going to say positive 2,800 kilojoules over 8.314 to 98.15, still the same temperature. And this is equal to a negative 1.13, which is equal to the natural log of K. If we do exponential to negative 1.13, this equals the 0.32 in the textbook, right? That shows 0.32. So, now we just kind of have experience doing it both ways. Which way the reaction is going, things to keep in mind here is definitely watch for these here because we need them here. So watch out for those when we're doing enthalpy, entropy, free energy. Okay. Uh, right? Know how to do this, right? Know how to get out of natural log, right? So those are things we do want to be aware of. But this will finish up chapter 13, and then chapter 14 will be next week. I'll open it up before we have the exams. I'll put the lectures out there before the exam next week, right? But that's it. Thanks.